Okay, let's continue on with part B of the I's habit, our lesson about complex numbers. Our next topic is to talk about complex conjugates. Complex conjugates are two complex numbers whose real and imaginary parts are the same except the imaginary parts have a different sign. So it looks like the sum and difference of the same two terms if it were real numbers with a variable I. But these are different complex numbers. A plus bi, a minus bi are examples of complex conjugates. How these are helpful, I guess I'm going to go back here. I'll show you if we take two complex conjugates and multiply them together, something rather interesting results. So if I take, say, 2 plus 3i and multiply it by its complex conjugate 2 minus 3i. From the last example, we looked at something like this with the sum and difference of the same two terms. It's a difference of two squares, so we don't have to do FOIL with this. We can just square. If we did, the inners and outers would add up to be 0. I just want to be clear with that. But we don't have to because we know that that will happen. So 2 squared is 4. 3i squared is minus 9i squared. Again, I wrote the minus because it's a difference and a sum. Well, 9i squared is negative 9, so it's 4 minus negative 9 or 4 plus 9. Believe it or not, those two complex numbers multiplied together gives us 13, a real number. So if we had to express the quotient of these two in standard form, so this is the first time we're looking at dividing two complex numbers. Again, we'll bring up this pad, we'll clean it up, and we'll look at what our trick is for this one is. We're going to actually write the example down here. Negative 2 plus 5i divided by 1 minus 2i. Our trick is we'd like to write this in standard form, so how we can do that is we'd like the denominator to be real. So what we realize is if we multiplied it by its complex conjugate, 1 plus 2i, we're sensing, we figure we're going to get a real number because that happens, right? Our inners and outers drop out, we've got the I squared, it becomes negative 1 and so on. So all we can do is multiply the numerator by the same complex number. So really we've taken this expression of a complex number divided by a complex number and multiplied it by 1 in the form of 1 plus 2i divided by itself. So up top we get a trinomial, which is negative 2 times 1 is negative 2. Then our outside terms would be minus 4i. Our inside terms is plus 5i. And our last would give us plus 10i squared. Right? Down below, this is the fun part, down below we just say it's 1 minus 4i squared. Well, 1 minus 4i squared is 1 plus 4 or 5. Gotta save that down here. I think I'm going to need some room for this. Then up here, this term is negative 10, right? Because I squared is negative 1. So we've got, I'll do it over here, negative 2 minus 10. And then we add the two imaginary numbers together, negative 4i plus 5i is plus I. So that would be negative 8 plus I. Now I'm not circling this yet because this is not in standard form. Notice the directions say we want to write this in standard form. So to write in standard form, we'd write negative 8 fifths, that's negative 8 divided by 5, plus 1/5 I. And that number now is written in standard form. So complex conjugates become real important when we want to try to do division with complex numbers and not have a denominator be a complex number. Well, we're going to define the square root of negative numbers in the following way. We're going to define the square root of negative b in terms of complex numbers to be I times the square root of b. Remember, I is equal to negative 1, so because I times square root of b squared is equal to I squared times the square root of b squared, and the square root of b squared is b, I squared being negative 1, we define the square root of a negative number to be simply the square root of that number, if it were positive, times I. So we're going to practice writing some of these numbers, some of these complex numbers as writing each of these complex numbers in simpler form. So what we're doing is remember I told you that just about all the arithmetic rules hold. So before we look at these, I need to share with you the one that doesn't hold is when you're multiplying two numbers together as radicals and you say, well, it's the product of those two numbers. That works if they're real numbers. It's valid for positive real numbers, but it does not hold when C and D are negative. As an example, if it did hold, we'd say that square root of negative 20 times the square root of negative 5 would be equal to the square root of positive 100, which is 10. However, we know that the square root of negative 20, by definition of complex numbers, is I times the square root of 20. And the square root of negative 5 is I times the square root of 5. Because remember, they're not real numbers, so we can only express them as complex numbers, and there are these two imaginary numbers. And if we follow these rules now, like we did with our earlier examples, I times the square root of 20 times I times the square root of 5 is I squared times the square root of 20 times 5, which is negative 1 times the square root of 100, which is negative 10. So if you followed what you thought was the right way of doing it, you'd think that these two would multiply to give us 10, but they don't. They multiply to give us negative 10. So again, our original directions are to write each of these as a complex number. So let me bring up this pad, clean it up. And let's do, we got a few examples to do. We'll do 3 examples. First one is going to be the square root of negative 5. Well, the square root of negative 5, again, anytime you want to take the square root of a negative number, you simply write I as a factor, and then the other factor is the square root of the number if it were positive. Now, again, we write it like this as opposed to the square root of 5 times I like this. If you looked at it, someone might think, although we know it's not, someone might think that I belongs as part of the radical, and that would be quite a different story. So you're going to find that whenever we have I be multiplied by a real number that's a radical, we're going to write first. Okay, so that's the first example we look at. We started with that, we end up with this. Second example will be a little more complicated. It's going to be 2 minus the square root of negative 11. Let me extend that radical sign. There we go. Divided by 5. And you can see this looks almost like what you'd see for a solution to a polynomial equation that's a quadratic. But right now we're just going to treat it as 2 minus I times the square root of 11 divided by 5. We can say 2. Which this would be equal to 2/5 minus I times the square root of 11 over 5. So again, here's our real number part, 2/5, and our imaginary part is square root of 11/5 I, negative times that. So that would be simplified. And the next example is as follows. 1 minus the square root of negative 16 times 5 plus the square root of negative 36. Negative 36. Okay, so before we could go ahead with our multiplication, we have to be careful of this, right? Because square root of negative 16 and the square root of negative 36 cannot be multiplied like we would if they were both positive radicands. So we're going to first of all simplify this as 1 minus I times the square root of 16. Square root of 16. And this would be likewise 5 plus I times the square root of 36. And now these two are perfect squares. The radicands are perfect squares, so it's 1 minus 4I times 5 plus 6I. And now we can progress like we would and we did an example like this, I think, in our last video, but 1 times 5 is 5. Our outers would be plus 6i. Inners, negative 20i. And the last product would be negative 24i squared. Okay, well, these two give us negative 14i. These two terms right here, negative 14i, right? And then the 5 is now added to 24 because negative 24i squared is plus 24. So we have 29 minus 14i, and that's in standard form. Okay, so that was our third example. So we'll end with finding all solutions to this quadratic equation, and not surprisingly, if we did find the discriminant, it would be a negative number. So there are no real solutions to this, but now we're thinking complex number system, so there should be solutions because we can get over the fact if we have a negative underneath the radical sign. So we're going to use the quadratic formula. A is equal to 3, B is equal to negative 5, and C is equal to 13. So x equals the opposite of b, which would be, I should say x equals the opposite of b, which would be, wow, let me fix that now. Yeah, let me fix that with an eraser. X equals the opposite of b, which is 5, plus or minus the square root of 25, that's b squared minus 4 times a times c, all divided by 6. Well, our numerator is 5 plus or minus the square root of 25 minus 12 times 13, let me save you the trouble, is 156. Now, again, if we're thinking real numbers, we'd say, let's stop right now, there's no solutions, but we don't stop now because we know that although there are no real number solutions, there are complex numbers solutions. So 5 plus or minus the square root of 25 minus 156 would be negative 131 all over 6. Again, notice there's a negative number there. No real solutions, but we can write this as 5 plus or minus I times the square root of 131, all divided by 6. And if we want to write our solutions in standard form, x would equal 5, 6 plus I times the square root of 131 over 6. Now let's write that better than that. Square root of 131 over 6, and x equals 5, 6 minus I times the square root of 131 divided by 6. Those are our two solutions. They are complex numbers, and I don't know if you noticed or not, but they are complex conjugates. We've got a plus bi, a minus bi. These are complex conjugates, and it's something to note, kind of important point, is that if a plus bi is a solution of a polynomial equation with real coefficients, then its conjugate, a minus bi, is also a solution, which is very helpful because if we found one complex number, we always know that if it is a solution, its complex conjugate will also be a solution, and that's what happened with this example that we just completed. So that's the end of both parts A and part B of lesson 4.5, complex numbers. We'll do a fair amount of these tomorrow in class. See you then.